Good morning, dear ladies and gentlemen. My name is Sergiy Fialko. I present the Krakow University of Technology as well as the software company SCATSoft from Ukraine. The title of my report is presented in this slide. We solve the natural vibration problems of structural and solid mechanics, and we use the finite element method. So we obtain the algebraic generalized partial eigenvalue problem 1, where K is a symmetric positive definite stiffness matrix, M is a symmetric semi-definite mass matrix, lambda is a diagonal matrix of eigenvalues, and V is a rectangular matrix consisted of eigenmodes V1, V2, and so on. We apply the model mode as well as the seismic mode. In model mode, we determine the required number of eigenpairs, you see the eigenpairs, and small it is the required number of eigenpairs, and large is the dimension of problem. In seismic mode, we determine eigenpairs until a required sum of model masses for each of seismic input directions O, C, O, Y, O, zeta is achieved. The sum covers all extracted eigenmodes. Gamma is a so-called mass participation factor. I dir it is a unit vector of seismic input directions. M dir total, it is a total mass and direction. And we consider problems with such ranges of parameters: dimension of problem and number of required modes. Where n is close to this value and n small close to this value, we obtain a very hard computational problem. There is presented the features of proposed block subspace iteration method. This method is focused on modern shared memory multi-core computers. Then, the dimensionality of the Krylov subspace remains constant, unlike the block-Lanzas method. This fact improves the load balance between threads. Then, the large frequency interval is divided into relatively small independent subintervals using the shift technique and ensure a quasi-linear dependence of computation time from the number of required eigenpairs, and then the spectral transformations improve the splitting of the closed natural frequencies and accelerate convergence. When we use the spectral transformation, we obtain a following formulation of the algebraic generalized eigenvalue problem. Here sigma is a shift. We create a subspace with dimension of m small. The rectangular matrix Q consists of its approximations of eigenvectors V1, V2, and so on at the iteration step K. On each iteration step, we make the inverse iteration step 5 and obtain the improved approximations of its vectors. And then we evaluate the subspace projection matrices K and M using the projection matrix Q and solve reduced eigenvalue problem on subspace and obtain a new approximations of eigenvalues lambda and approximations of eigenvectors on subspace Q. Then we make a prolongation of reduced eigenvectors onto source level and obtain the improved Ritz approximations at the next iteration step K plus 1. Comments. The inverse iteration step 5 is responsible for the convergence of entire method. Steps 6 and 7 ensure the orthogonality of the improved vectors Q bar to prevent the convergence of all vectors in the block to the lowest eigenvector. Let's expand the approximation of the eigenvector VIK on the exact eigenvectors VI of problem 4. And we obtain the expression 8. Let us substitute 8 in 5. And using the orthogonality conditions between eigenvectors vi, we obtain for each mod I the separate relations which connect the initial coefficients alpha 0 with the coefficients of this expansion at the iteration step k, expression 9. This expression demonstrates the main feature of the shifted inverse iteration. The closer the shift sigma is to the given eigenvalue lambda I, the faster the contribution of the coefficients alpha ik suppresses the contribution of the remaining factor in expansion 8. And the faster the convergence will be. There is shown the typical convergence of eigenfrequencies for methods based on shifted inverse iteration. You see that shift sigma imposes a centrum of convergence. The above version of the algorithm 567 suffers the disadvantage. With an increase in the number of required eigenpairs, the dimension of the block M increases, which leads at least to the quadratic computational complexity of the entire problem. To overcome this disadvantage, we apply a block subspace iteration method. This method, in this method, the frequency interval is divided into subintervals using shift value sigma, keeping a relatively small dimension of block M. There is presented the typical frequency interval, and for each lambda belonging to the interval left mark, right mark, the pairs lambda v are convergent and no skipped eigenpairs. As soon as the current interval left mark, right mark is determined, we pass to the next interval using the convergent and unconvergent Ritz pairs in the block located right from the right mark. And this pairs allows us to predict a new value of sigma, shift sigma. Sorry, I have, okay. This approach has a quasi-linear computational complexity. There is presented the general algorithm of the block subspace iteration method with spectral transformations. It is the initial approximations, initializations. This while loop runs until the criteria stop iterations will be fulfillment. On each iteration step, we check status of vectors in block Q. We make inverse iteration step. We create subspace projection matrices K and M. We solve reduced eigenvalue problem on subspace. And then we make a prolongation of the vectors, eigenvectors from subspace onto initial space and calculate new Ritz vectors and pass to the next iteration step. In model mode, the criteria stop iteration is presented here. The number of convergent modes must be not less than the number of required modes. In seismic modes, we must achieve such values of sum of model masses in each seismic direction, which is not less than required corresponding values. There is presented the algorithm 2, which checks status of vector in block Q. In the first parallel region for each iterated mode I, we evaluate the residual vector R and compute the norm of relative error. If this norm of relative error is less than required tolerance tau, we mark this mode I as a convergent. Otherwise, we mark as unconvergent. Then we call the set shift procedure. This procedure checks does all reads pairs in the interval between left mark and sigma are converged. If yes, this procedure determines the right mark. It is the first unconverged reads pair. And then, using the increment h vec parameter, evaluate a new value of shift. Increment h vec parameter implicitly implies onto computational stability of entire method. If set shift procedure detects the unconverged reads pairs in the interval left mark and sigma, this means that the current frequency interval left mark right mark is impossible to be closed, and this procedure returns the previous value of shift. If we obtain the previous value of shift, we break this algorithm and continue the next steps in our main algorithm 1. Otherwise, if set shift procedure returns a new shift value, that means that we pass to the next frequency interval. It is such a situation. And we store all converged reads pairs between left mark and right mark as the final result. We pass to the next frequency interval, item 15, and in second parallel loop, we generate new start vectors at the positions of the converged eigenpairs, produce their orthogonalization against themselves and against all remaining vectors in block, and make such a normalization. Multithreaded parallelization. First of all, we use a highly parallelized parfait solver for multi-core computers. For factorization, the shifted matrix K minus sigma n as soon as there is a change in the shift value sigma when passing to the new frequency interval. Then, the forward-back substitutions during inverse iteration step in parfait solver are parallelized and are especially efficient for multiple right-hand sides. Then, we parallelize the calculation of the subspace projection matrices K and M. There is shown the subdivision of the block Q onto parts. On this example, we demonstrate it for 4 threads. And in parallel region, we simultaneously multiply the matrix K by parts of this block Q and obtain the auxiliary buffer BIP. IP it is a thread number. Then we multiply the transposed matrix Q by corresponding block, auxiliary block BIP on the same thread IP, and obtain the corresponding part of the subspace projection matrix K. Exactly the same we obtain the subspace projection matrix M. Then, the calculation of residual vectors and new start vectors in block is parallelized. It is the first parallel region and second parallel region. And then, when we calculate the new reads vectors here, we use a multi-threaded version of the GEM procedure from Intel Math kernel library. Numerical results. Numerical results have been obtained of computer with 12-core Intel i9 processor. You see the amount of core memory, and there is presented the general characteristics of this processor. Figure 4 demonstrates a design model of multi-story building with more than 4 million equations. The 500 eigenpairs are extracted, and such number of eigenpairs allows us to satisfy the requirements of seismic codes, namely the sum of model masses in each seismic direction must be not less than 19%. In table 1, we present the durations of the separate principal stages of our approach, as well as the duration of total approach on several threads. It is a duration of check status stage of vectors in Q block. It is the duration of factorization. It is the duration of forward back substitutions. It is the duration of subspace matrix projection. It is the duration of evaluation approved Rivets vectors. The rest part of algorithm is parallelized partially too, and it is a total duration. In last row, we demonstrate the speed up for each stages of our approach, as well as speed up for entire approach on 12 threads. We compare these results with block Lanczos method with spectral transformations, which many years is applied in SCAD software. This method, Lanczos method, uses the same parfait solver. You see here the principal stages of the block Lanczos method and corresponding durations and speed up on 12 threads. For our approach, we obtain the total computing time on 12 threads, essentially less than for a block Lanczos method with spectral transformations. Then, the total speed up on 12 threads is almost 2 times more comparing with total speed up of block Lanczos method with spectral transformations. The next example presents the design model of industrial building comprises about 2 million equations. The bearing system of this structure consists of cross walls and floors, which generates a huge number of local vibration modes, which practically do not contribute anything to the sum of model masses. To achieve 19% the sum of model masses in all the seismic input directions, we need to evaluate more than 20,000 eigenpairs, so it is a very hard computational task. There is presented the duration time from block subspace iteration method, and duration of the block Lanczos method is essentially more. There is shown the dependencies, the sum of model masses in each seismic direction versus the number of convergent eigenmodes. Starting with this point, we obtain a very slow convergence. And the last example presents the design model of multi-story building about 2 million equations. And this design model comprises a lot of practically the same floor slabs. Such peculiarity of these structures leads to the following fact. We obtain a very dense spectra of eigenfrequencies because almost the same slabs demonstrates practically the same eigenvalues. You see the typical natural vibrations mode in vertical direction of the single floor slab. There is presented the fragment of eigenspectrum, and red color denotes the almost multiple eigenfrequencies. Such a situation essentially complicate and slow down the convergence of the eigenvalue solvers. There is shown the dependence of the sum of model masses versus the number of convergent modes. You see the especially slow convergence for sum of model masses in vertical direction m O zeta. The duration time of block subspace iteration method is presented here and is less than duration time of block Lanczos method with spectral transformations. Conclusions. The first two items are multiple underlines for today in my report, and then the proposed approach focused on multi-core computers with shared memory demonstrates how high computational stability and stable speed up with an increase in the number of threads. Thank you very much for your attention.
Thank you. Of course, we have some little time for questions. So, if there are any questions, please ask. I have some, but first I would like to ask other people. I can't see any any hands or so. I have some little questions. First, the matrix is the main matrix is sparse.
Yes, of course, it is a finite element method and
yes.
all.
Yes. Okay. It was only for clarification. You used a processor with 12 cores, yes?
In this example, yes.
And my question is, have you used more threads than cores? Because you have said about only 12 threads. And my question is about hyperthreading. Is it sensible? Is it can it be faster if we use more threads, because Intel is with hyperthreading, so theoretically up to 24
yes.
threads could be used to speed up the computations. However, our experiences with hyperthreading are not very good. So my question is, did you test for more threads?
Yes, of course. Yes, of course. This processor supports the 24 logical processor. The operating system sees 24 logical processors, but if we try to use hyperthreadings, first of all procedures from Intel mass kernel library, for instance, the DGEM procedure, restricts only by 12 threads automatically. It doesn't depend for us. It is an Intel peculiarity then. We try to impose the more threads than number of physical cores. And often we obtain the little degradation of speed up in such a situation. Then we try to bind the threads when we use the 12 threads onto onto logical processors to avoid the situations when on one physical core works two threads. And in such a situation, for single task, and we use our computer only in monopoly mode, we obtain a slightly better results. But it is very dangerous approach for workstations, which can work simultaneously several problems.
Okay, thank you. That experiences are very similar to ours. We will talk about this in the next presentation. And one more question about accuracy of this method and Lanczos, which is better, because you compared the speed of Lanczos and this method. So what are the accuracy of this?
Accuracy practically the same, because if of course if you we accept the same tolerances, but accuracy is practically the same because we control the norm of residual vectors.
Yes, so it is given at the start. Okay. Thank you very much.